For decades, the elusive holy grail in Parkinson's disease research has been finding a way to repair faulty dopamine neurons and put them back into patients, where they will start producing dopamine again. Researchers have used fetal material, which is difficult to obtain and of variable quality. Embryonic stem cells represented a tremendous innovation, but making dopamine neurons from stem cells is a long process with a low yield. These issues have driven researchers to try to develop ways to turn cells that are easy to obtain, such as skin cells, into dopamine neurons, which are normally hidden in the brain. But here, too, it has been difficult to obtain sufficient quantities of neurons. Now, Parkinson's disease researchers at the Jacobs School of Medicine and Biomedical Sciences at the University at Buffalo have developed a way to ramp up the conversion of skin cells into dopamine neurons. They have identified, and found a way to overcome a key obstacle to such cellular conversions. At the same time, the researchers say the finding has profound implications for changing the way scientists work with all cells. The new research, published December 7 in Nature Communications, revolves around their discovery that p53, a transcription factor protein, acts as a gatekeeper protein. We found that p53 tries to maintain the status quo in a cell. It guards against changes from one cell type to another, explained Jian Feng, Ph.D., senior author and professor in the Department of Physiology and Biophysics in the Jacobs School of Medicine and Biomedical Sciences at UB. We found that p53 acts as a kind of gatekeeper protein to prevent conversion into another type of cell. Once we lowered the expression of p53, then things got interesting. We were able to reprogram the fibroblasts into neurons much more easily. The advance has importance to basic cell biology, Feng said. This is a generic way for us to change cells from one type to another, he said. It proves that we can treat the cell as a software system, when we remove the barriers to change. If we can identify transcription factor combinations that control which genes are turned on and off, we can change how the genome is being read. We might be able to play with the system more quickly, and we might be able to generate tissues similar to those in the body, even brain tissue.